Okay, hello maths fans. I hope this is working. I'm going to assume it is, unless anyone writes me a very, let's say, angry comment saying, we can't hear you or we can't see you. So thank you very much for tuning in. It's my first ever time doing something live, so we'll see how it goes. The idea here is on Monday, we released the first Tom Rock's Maths Appeal video looking at GCSE Maths. And we were talking about percentages, decimals, and fractions. So the main purpose of the live stream is for everyone to hopefully take part and give me questions based around the topic that we were discussing in the video on. So, though I will take other maths questions as I see fit, we'll see. But I am going to start with some based around percentages, decimals, and fractions. So I've had quite a few sent in beforehand, so I'm going to work through a few of those to kick things off. And whilst people are still joining, and I guess we're all sort of getting used to how this whole works, at least I'll be getting used to how this whole thing works. So I'll start off by answering some of the questions sent in, and then we'll move on to, if you have any questions during that, just type away in the chat box. I can see the chat box. I do have it open on my computer, so hopefully I'll be able to respond, and we can sort of take part in a bit of discussion. I have no idea how long this is going to last. Till I run out of questions, till I get bored, till we all get bored, who knows? So the first question I want to look at was what somebody, actually I know who sent me this, let me have a look. So this one is from Sarah, who is in Northwich. So hello Sarah in Northwich. I don't know if you're watching or not, hopefully you are. So you sent me a question which said, how do you convert a recurring decimal into a fraction? So I need a recurring decimal. Does anyone want to give me a recurring decimal? So does anyone want to type a recurring decimal into the chat box? That would be great. Otherwise, I will just make one up off the top of my head and then go with it. I'm waiting for a few more seconds. Otherwise, I'm going to make one up. Okay. Right. Oh, no. Oh, we've got one. Great. Yes. Okay. 1, 2, 3. 1, 2, 3, 1, 2, 3. We're going with that one. One was very good chat. I appreciate the joke. Right, so we've got, let's go with 0.123, 123, 123. And this is going to go forever. So you can think of this as 0.123 recurring. Now, to turn this into a fraction, the trick is basically we have to get rid of this infinite expansion. So this is the ... here is telling you that this is going forever, and this will just continue indefinitely. And we can't really deal with that infiniteness in its current form. So the trick here is always, can you create something that's similar to this number, still with an infinite decimal expansion, and then take them away from each other? So to do that, given here we have 3 places which repeat, so this is 3 repeating places, what we do is we multiply by 10 to the power 3. So, and if this was n places that were repeated, so 5 or 6, whatever, any value of n, then you would multiply by 10 to the n. So here it's 3, so you multiply by 1,000, 10 to the 3, and that shifts everything 3 places. So you get 123.123, 123, 123, blah, blah, blah. And now we've got another infinite decimal expansion, another recurring decimal, recurring number, but it's the same as the one above past the decimal point. So this is where you say, well, if I call this one x, then this one is now 100. Hang on. So if this is x, then this one was 1,000x, wasn't it? Because we multiplied by 1,000. It's equal to this. So if I subtract x from 1,000x, I'll get 999x equals 123.123.123.123 minus 0.123.123.123.123 is going to get rid of the decimal place. So this is now equal to 123. And so x, which was our original decimal, is now just 123 divided by 999. That might be, you might be able to simplify that. I don't think you can simplify that. Does 123 have any factors? That's a question for you all. Maybe we can simplify that. I don't think we can, but maybe you can. But either way, we've now turned our recurring infinite decimal into a fraction. Okay, right. So that was the first question. Thank you, Sarah, for sending that one in. Now, another one that I really liked. Let me just check who this one is. Someone has told me we can divide by 3. So we've got 41. Yes, very nice. So divide 123 by 3. Yeah, very nice. I in my head, I did think maybe we could divide by 3, because this you definitely can divide by 3, but for some reason I decided you couldn't divide that by 3. This is what happens when you do things live. So yeah, you're right, very good. So that will actually be 41 out of 333. And that is definitely the simplest fraction, because this, is this a prime number? I want to say yes. I want to say 41 is a prime number. I'm not thinking. If 41 isn't a prime number, I'm sure someone can tell me. I'm pretty sure it is. So we're going with this being the simplest fraction. But we didn't have to do that. We could have just left it here, and we still got rid of this infinite recurring decimal as a fraction. Okay, so the second question that I wanted to talk about, because it was a really nice question. So this was from Matt, who is in Bournemouth, also in the UK. Hello, Matt. Thank you for your question. So this was asking about percentages and repeating a percentage increase forever. So this is actually a really, really interesting question. It sounds quite innocent at the beginning, or reasonably straightforward, and then it gets very, very sort of in-depth, or at least I got very in-depth with it. So Matt's question was, what happens if you increase a number by 10% forever? Increase by 10% forever. So again and again and again. So you start with some number, you increase it by 10%, then you increase by another 10%, then another 10%, and another 10%, and you just keep going and going and going. Right, so what we're going to do here, it's a bit wet, is we're going to start with our number being x. Okay, so this is our number that we're going to increase by 10% again and again and again. So when we increase it by 10% once, what we're doing is adding 0.1 lots of x onto it, which will give us 1.1 lots of x. So that's after one iteration of increasing by 10%. Now, if we do this again, we're going to then have 1.1 x plus 0.1 x. No, it's not going to be x, though, is it? It's going to be plus 0.1 times 1.1 x, which is going to be 1.21 x. Okay, I think. I'm sure you can all check my mental arithmetic. So now, so we're seeing that we started with x, then we got 1.1 lots of x, then we have 1.21 lots of x, and this is going to continue. But we can actually, hopefully, spot a little bit of a pattern about what's going on here. So this is 1.1 times x. Now, this number looks very much like 11 times 11 squared times our original number, x. So if we are to just continue this forever, we're just going to get, the next stage would then go to 1.1 cubed times x, then 1.1 to the fourth times x, etc., etc. So we'd end up with 1.1 to the power n x after n steps. Right. Now the next question is to wonder about, what does this actually equal? So we have a formula here which tells us the value of x after n increases of 10%. So what we want to think about is, could this go to infinity? Could this keep growing forever and ever? Or could this go down to 0? Could it keep shrinking? And what's going to determine that is going to be the value of x. So as a simple case, if we considered x to be 1, for example, so let's take an easy case. If x is equal to, this is 1.1 to the n. So if x is equal to 1, then this is just 1.1 times n amounts, and so that's actually going to go to infinity, tend to infinity, because it's just going to keep increasing forever and ever and ever. And you can try this. You can do a plot of the graph. If you plot, I think I did plot this. Let me just think about what it looked like. Yeah, so if you plot the graph of y equals 1.1 to the power of x, it basically, so it's going to start at 0. It looks like that. It's an exponential graph, which we're seeing a lot at the moment, right? There's all this discussion of exponential graphs with diseases and whatnot. So you have this exponential graph of 1.1 to the x. So it does when it's just up here. Now, but over here, we're considering different values of x and then letting n go to infinity as we repeat this percentage increase. So if I now take x, for example, to be, what could I take this to be now? What if I took it to be a half, for example? Then that will still, actually, will that be okay? Ooh. It's going to depend on whether x is taken to many powers. So how did I do this before? Okay, right, let me go back a second, because I've managed to get a different formula to when I was thinking about this before. Again, classic, doing this live. It's so much easier when I'm pre-recording a video. All right, so I agree with this. 1.1x plus that amount of x is definitely that. But what can we do here is we can say, okay, let's think about this. Let's say, right, let's try something a little bit different. So if we have x plus that. So this is now, so this is our starting value. And then we're going to add on 10% of x, which is the same as adding on 1/10, right? So 10% is equal to 0.1 is equal to 1/10. So percentages, decimals, fractions. So here we have this number. And then what we want to do is repeat this several times. So I think that's actually what we want to do, isn't it? So if I just repeat this once. Okay, let's do this. This is more interesting. Let's look at this one. So this is kind of like compound interest. So let's consider this formula instead. So now what we can do, so it's the same thing. We can take the x factor outside the bracket, and we have x to the n times 1.1 to the n. So slightly different to what I had before. I was missing this n up here. So I'm not quite sure what I did before. But anyway, as I said, we're going to go with this version. This version is way more interesting. And lets me talk about my favorite number, as we'll see. So we've got x plus x over 10, all to the power n. So we take out the factor of the x. So you can, just to break that down, what we're really saying is this is x times 1 plus 1 to the 10th, all to the power n. So now this n will go on this bracket and this bracket separately, and so you get this one. Now, we know that if x is 1, then this is just 1.1 to the n, and we know over here this goes to infinity. But now if x is a half, what we've got here is we've got this thing which will go to infinity, as shown on our graph, but then we've got a half to the power n. So if you plot the graph of, okay, so if I make that one n, and then this is 1.1 to the n, and then this is going to be half to the n, and this is now n. So if we plot the graph of a half to increasingly large powers, what you see is it gets smaller and smaller and smaller. So a half squared gives you 1/4, 1/4. A half cubed gives you 1/8. A half to the power 4, 1/16. They're getting smaller and smaller and smaller. So you're basically decreasing away something like that. So we've got one term here, or this 1.1. This term wants to go to infinity, and this term wants to go to 0. So then the question is, who's going to win in that race? You've got one term's trying to make things really big, and the other term's making things really small. And we want to know, does the big one win? Do we get to infinity? Or does the small one win? Do we go to 0? Or are they kind of the same, and maybe we get some finite value in the middle? We don't really know at this point. So what we can do is we can start playing around with different values. So the one that, if we plug in a half, for example, so if we go back to this formula here and plug in 1/2. So if x is a half in this formula, we've got 1/2 plus 1/2 divided by 10. So that's 1/20th, all to the power n. Now, a half plus 1/20th is going to be 11 out of 20. So that's 11 out of 20 to the power n. And this will definitely go to 0 because this is less than 1. So as you take this number, this fraction, to larger and larger powers, it's just kind of the same as the half graph. It decreases and goes to 0. So this one goes to 0. Okay. So a half goes to 0. Right. Does anyone want to give me another number to try? Type a number between 0 and 1 in the chat box that might be an interesting one to look at. Ideally bigger than a half, because we know that a half. Right, I've got 3/4. Thank you very much, Seal. Great name. Right, so 3/4. So let's do a similar calculation to what we did here with the number 3/4, 0.75. So this one is going to give us 3/4 plus 1/10 of that, 3 out of 40. So that's 30 out of 40 to the n. So that's going to give me 33 out of 40 to the n. This is less than 1. This will now go to 0. Right, so this disappears. Okay, 33 out of 40 goes to 0. Okay, so 3/4 goes to 0. Right, what else have we got? 0.3 recurring, good one. 10 11s, let's go 10 11s, I like that. 10 out of 11, so it's less than 1 and it's bigger than 3/4. So 10 11ths in this formula here. So we've got 10 out of 11 plus 10 out of 100. 10, 110 to the power n. So that gives us 1 to the power n. So that goes to 1. Nice. Play Simon. Right, so 10 11s is going to go to 1 if we plug that one into our formula. So that is going to be the decisive number, really, isn't it? The 10 11s. So if we've got something that is, so what can we say? We had this formula. So we can say over here that, let's do this in pink. This goes to infinity if x is greater than 10 11ths. And it goes to 0 if x is less than 10/11, and it goes to 1 if x equals 10/11. Right, so that finally gives us an answer to the question. So we were looking at what happens if you increase a number by 10% forever. We got this formula here, which is super helpful. We considered some different values to figure out what was going on. Sometimes we went to infinity, sometimes we went to 0. And then we found, or Simon found, that when we have 10/11s, we get to 1. And so anything below that will go to 0. And anything above that will go to infinity. Okay. Right. So staying on this particular topic, let me just rub this off. I have a question for all of you. We're going to play a sort of make-believe game show. So right, so as I said, we're going to play a make-believe game show, which is going to have the following prizes on offer. So, option A, you can take a prize of £3. Option B, you can take a prize of £1 plus 1/12 interest every month. You can have option C, which is going to be £1 plus 1/52 interest every week. Or option D, you can have £1 with 1/365th interest every day. And the question is, which option do you select? Okay, so I'll give you, obviously you can just plug these into a calculator, but that's no fun. So let's not do that. Let's think about just looking at this. Type your answer in the chat box. A, B, C, or D. What would you take? And we'll see what everyone comes up with. Okay, so we've got two votes for D so far, right? Got those two tallies on there. I'll give you another few more seconds if anyone else wants to vote. Another vote for D. Okay. Another 2 votes for D. Okay. Apparently we're all going D. Okay. So it just sees everyone's going D, which is fine, right? You can do what you want in this situation. We've got some other votes now, right? Okay. I'll add these last set because we've got some different votes. We got D in the long run and A in the short term. Okay, interesting. So we've got let's call that half a vote for A and another half a vote for D. And then we've got A and B, okay, as well. We've got another one there, another one there. Okay, so basically we want to know which one of these is larger, so which is the biggest amount of money you're going to get. And we can do this using a formula very similar to the one that we just had when we were working through the percentage question, which is why this is linked. So £3 will always be £3 forever, right? So that doesn't change. So that is the final value you will get there is £3. Now, 1 plus 1/12, and then getting paid that interest every month. I've just realized. Well, this is only for for a year. I've just realized I probably for a year. Okay. Right, I've actually incorrectly defined the problem. We now have a new problem, which is you're only getting this for a year. Okay, so we're going to have to vote again and decide now that I've actually given you the correct problem. So now I see why somebody was saying we want A in the short term and D in the long term. Okay, so the idea is this is only going to happen for a year. I'm not going to keep giving you interest forever because then the number would increase forever and ever and be a lot more than £3. So the idea is, do you take option A, B, C, or D? So where it's for a time period of a year. So after a year with option A, you will definitely have £3. After a year with option B, you will have some amount which we can work out. Same for C, same for D. But just to start with, I want to know what people think. Right, so I've got 1 vote for A and 1 vote for D. Another vote for D, okay. Maybe it's not changing your thinking, but either way, I just wanted to make sure I did define the problem correctly to allow us to work this out. Okay, another vote for D, vote for A. Okay. Right, so if we try and work out all of them are the same. Well, that's an interesting answer. Okay, so we've got all of them as one option, represented by that square bracket. Nice. Okay, so it seems to be split between A and D, which is good because it shows that I think some of you have got a feel for what's happening here. So we're going to try and work out the amount we will end up with for all of them and then see which one would actually have been the best choice. So A is obviously going to be £3. It's not going to change. You get that £3 done. There's no interest. Now, for option B, what we can think about is sort of writing out a formula for what's happening. So this is compound interest. As I said, it's very similar to what we looked at with the percentages problem last time. So what we've got here is 1 plus 1/12. And what we're doing is we're taking this to the power 12. So we're starting with £1. We're adding on a 12th, and then we're doing that 12 times because we're doing it every month for a year. So this is going, you can work this out. Now we have fixed numbers. You can plug this into your calculator, which I did earlier, and you get £2.61. Okay. So we definitely don't want option B. So I don't think anyone voted for B. Even people coming in a bit late did not vote for B. So well done for not voting for B. It's between definitely less than the £3. Now for C, it's going to be very, very similar. Right, so we got the same formula, but now it's 1 plus 1/52. And we're doing this every week. So we're doing this 52 times over the course of the year. So that's going to give us, plugging that into your calculator, you get 2.71. Okay, I should maybe write these. I'll rewrite these underneath so it's a bit clearer. So A gives you £3. B gives you £2.61. C gives you £2.71. Right, so there's some kind of a pattern between B and C. So what's happening between B and C is we're getting paid a smaller amount of interest, but it's happening more often. So again, it's like the problem we discussed last time, where we had one term growing to infinity and one term that was going to 0. And we were trying to find out what's the balance between those two terms to give us the answer. So the same thing's kind of happening here. So we make the payments more often, but the amount you get paid is a little bit less each time, the interest. But you're seeing an increase overall. So then you might wonder, for part D, does the same pattern continue? Do we continue to get more and more, like our total being larger by paying a smaller amount of interest, only being 1/365, but now it's being paid 365 times. And when you plug part D into your calculator, which will be the formula, part D will be 1 plus 1 over 365 to the power of 365, you get £2.71. So it doesn't increase. The most you can win is £2.71. So the actual answer is definitely A. So well done to these 3 people who voted for A, and anyone else who I can see that lots of other A's have appeared. So well done for anyone who worked out that it was going to be number A. So what's actually going on here, and this links into my favorite number, which is tattooed on my arm here, is we're calculating the number E to more and more accuracy. So some of you, I think, spotted this. Somebody very cleverly said, are they allowed to vote for option E? Tom, well done, Tom, for spotting that the answer was option E. So what's happening, if you look at the terms in blue, the different formulas that we've got, what you're doing here is basically saying we have 1 plus 1 over n to the power n. So this is what we have in each case, where in part B, n is equal to 12. So here n is 12. Part C, n is 52. And part D, n is 365. And what we're doing here, or what you can do, is you can now take this limit as n goes to infinity. So you keep increasing n higher and higher and higher. So instead of being paid 1/365th every day, for example, you could get paid your interest every second, maybe, and there are 31,536,000 seconds in a year. So if you were to calculate for n equals 31,560,000, you would still get £2.71. So what you're actually doing is you're getting closer and closer to E, but we never get to £2.72. So the limit as this goes to infinity is equal to the number E, which is 2.718. And I'm going to just cheat and look at my arm for the next number. 2.7182818. It carries on. So as you increase n, you get closer and closer to this number, but you can never reach £2.72. So the numbers are increasing between C and D, but you just can't have a fraction of a penny. So you're stuck on that £2.71. So the purposes of the game show, you definitely wanted option A. Okay, right. I think that's probably enough of me talking about. Oh no, there's one final question I wanted to do because this was another great question, which is a quick one. This one was from Nicholas. So Nicholas asked me, what is my favorite fraction? So if anyone else wants to share their favorite fraction in the chat, please do. But my favorite fraction is so my favorite fraction is 3 divided by 2 to the power of 9/4. So this is my favorite fraction. You may be wondering, why on earth is this my favorite fraction? So this is actually from my my PhD research when I was looking at rivers discharging into the ocean. So there is a Numberphile video about this called Where Does River Water Go?, which I totally recommend you should go and check out. That will fill you in on everything you need to know. But in short, the idea is you have a coast and you have a river. So this is the land. And you have your river. And your water is flowing out of your river. And we want to know, where does this go? Where does this river water actually go within the ocean? Because there is a pattern to this. And I was trying to understand this mathematically. And basically what happens is it comes in, it forms a really big whirlpool, and then it flows along the coast. So this is what happens. You can see this in real data. So I actually went on board a ship and sailed around the ocean for 6 weeks, which is a very long time to be on a ship. I can tell you that. And we're studying this, and we found data that supported the models. I saw this in my experiments. And so what I was trying to understand were some of the properties of this current that forms along the coast. And one of those properties is the velocity of this current. So the velocity of this current, this river water flowing along the coast, is equal to the rotation rate times the density difference times the amount of water leaving the river, all multiplied by 3 divided by 2 to the 9 quarters. So I did this, sort of went through this calculation in my thesis, which is on my website if you want to check that out as well, and sort of derive this number through various integrals and various formulas. But this tells you the speed of the river water as it flows along the coast, and this number just happened to appear, and so it then instantly became my favorite fraction. So that is my answer to Nicholas's question. So if any of you have favorite fractions with a reason, do share them. It'll be fun. I don't know if I've ever been asked my favorite fraction before. So as soon as I thought about it, this was the obvious answer. But you know, it's an interesting question. Okay, so I've gone through lots of questions people sent in beforehand. So I guess I'm now happy. If anyone else currently watching wants to ask any questions, then let's go with that and see what we can do. So if you've got any questions at all, ideally let's start with the percentages, decimals, and fractions ones. That would be great. But if there are other questions, then maybe we can do some of those as well. We'll see. Okay. What is my favorite proof? Oh, that is a good question. Favorite proof. Favorite proof would probably be. I'm trying to think of one that I can do off the top of my head as well. Would be nice, wouldn't it? Okay, so I'm going to rub the board off whilst I try and think about what my favorite proof is. Okay, I've got one for you. Okay, I don't know if this is my favorite proof because it's not, mainly because I'm not sure it could necessarily be called a proof because it's not super rigorous. But I'm going to call it, let's pretend it's like a pseudo proof, and it's definitely my favorite one of those. Okay, so we're going to look at the following sequence: 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus. And this is relevant to fractions because these are all fractions. So I can totally talk about this during the percentages, decimals, and fractions live streams. It's very relevant. So what we want to do is we want to calculate the value of this sum. Now, I'm sure some of you will have seen this before. So if anyone wants to tell us all what the answer is, I'm then going to show you how to prove that is indeed the answer. So I'm just going to write the sort of the symbol notation or mathematical notation for this would be the sum from n equals 1 to infinity of 1 over n. So here you've got n equals 1. This one is n equals 2. This one is n equals 3, etc., etc. Okay. It is not minus 112. That would be 1 plus 2 plus 3 plus 4 plus 5, etc. This is 1 over n rather than just n. Okay, we've got a favorite fraction, 1/6 to the power of 1/6. Love it. That's a good one, Francesco. Same as me, it comes up in your work. That's nice. It's unfortunately not 2. So the one that equals 2 would be if you do the sum from n equals 1 to infinity of 1 over 2 to the n. And this is actually going to be important, so I'm glad you mentioned this, because this one is going to be 1 plus a half plus a quarter plus 1/8 plus a dot. Now this one is a geometric series. So we actually have a formula for this. So this has a common ratio, which means that to get between terms, you just multiply the last term by the next one. So to go from that term along, you're multiplying times a half, etc. So your common ratio is equal to 1/2, and your geometric series formula tells you that the sum is therefore equal to 1/1 minus r, which here is going to give you 2. Well, I'll write out that last step just to make it more obvious. So it's 1/1 minus r, which is 1/1 minus 1/2 is 1/2, which is 2. So this one is 2 from using our geometric series formula. But now the top one, we don't have a common ratio here. There isn't a number that you multiply by to get from any term to the next one. So to get from this term to this term, you multiply by 1/2. But then if you multiply a half by a half, you get a quarter. You don't get the 1/3. So there's no common ratio between all of these terms. So we can't use geometric series on this top one. So anyone have any ideas what the top series is equal to if we add it up forever? So we've got one suggestion of saying it's finite, which is actually, unfortunately, not true. It goes to infinity. So this goes to infinity. Okay, and one way we can think about this is actually using this, my proof that I'm going to talk you through, which is one of my favorites, is using this series here about 1/the powers of 1/2. So the proof goes as follows. As I said, this is more of a pseudo proof. This is not super rigorous, but it'll give you a feeling of what's happening. So, right, let's just, no, I can leave them all on the board, I think. Okay. So what we want to do is start off by comparing terms in each of these sequences. So we've got, let's think about this. This is 1, it's a half, it's a quarter. So what I can say is, if I take the first term here, the 1, and then we compare this to, let's say, this term in this second one, 1/2. So 1 is definitely bigger than 1/2. So 1 is bigger than 1/2. Now this is a true statement. Now, if I go and take this term plus this one, maybe I should do this in a different color so we can emphasize they're going together. So now, I'm going to take these two terms together. So 1/2 plus 1/3. And I'm going to say that those two together are bigger than 2 of these, are bigger than 1/4 plus 1/4. Okay, so you can either think of it as comparing to the terms in this sequence, or you can think of it as saying the next term along. So we said that 1 is bigger than 1/2, which is true. And then we've taken the next 2 terms, and if you replace each of those by a term further along, then because it's further along in the sequence, it's definitely smaller. So you replace each of those 2 by 1/4, then you have 1/4 plus 1/4. And you can check this is true, right? So 1/4 to 1/4 is 1/2, and a half plus a third is bigger than a half, right? It's like 0.8 something. 0.83333. There you go, 5/6. So this is also true. And now we're going to do the same thing again. Do this in orange. So we can do the same thing again with the next, it's going to be the next the next 4 terms. So we're going to have 1/6 and 1/7. So we take those 4 terms, a quarter plus 1/5 plus 1/6 plus 1/7. And if we replace each of them by 1/8, then the left-hand side is bigger, because 1/8 would be the next term along, so it's smaller. So this one is now 1/8 plus 1/8 plus 1/8 plus 1/8. Okay, and then we carry on. So this is the start of our pattern. And we're going to allow this to sort of go forever. So if you now add up everything on the left-hand side of the inequality, so 1 plus a half plus a third plus a fourth, a fifth, a sixth, a seventh, and keep going, what we see is that the left-hand side here is equal to our sum. It's equal to 1 plus a half plus a third, fourth, fifth, sixth, seventh, forever. And we know that this is bigger than everything on the right-hand side. So the right-hand side is equal to a half plus a half plus 1/8 plus 1/8 plus 1/8 plus 1/8 plus another a half. And this is going to go on forever. So we've got an infinite number of inequalities. And for every inequality, the right-hand side is a half. So the right-hand side is equal to, or I should say tends to, a half times infinite number of times, in some sense. So what we've got, a half times infinity is, of course, infinity. So what we've shown here is that the left-hand side is the sum we want to calculate. The right-hand side is infinity, and the left is bigger than the right. So this, our sum of 1 over n, must be infinity, because it's bigger than infinity. So therefore, it is infinity. So I wouldn't say it's a super rigorous proof. As I emphasized at the beginning, it's more like a pseudo proof. You would need to define a bit more like what you meant by these limits and the idea that you can take, inequalities forever. So there's like some levels of rigor that are needed to make it a formal mathematical proof. But it's my favorite sort of pseudo proof, as I said, that I can show you as well off the top of my head. So great question. Okay, right. I've been going for 52 minutes. I reckon I might as well do an hour at this point. So we can do 1 or maybe 2 other questions. So any other questions? You've got a few more minutes to, drop them in the chat box. I don't think anything else was thrown in. Oh, one I can do quite easily. What have we got here? What sort of range was the Reynolds number of the river problem? So the water in the river is going to be turbulent. So the Reynolds number would be over 1,000. So generally, if the Reynolds number is over 1,000, then that is pretty much turbulence. If it's over 3,000, it's definitely turbulence. So orders of magnitude, the Reynolds number is around 1,000. In the river problem, because rivers are turbulent, basically. And I saw that as well in my experiments when I was recreating the situation in the lab. I also had a Reynolds number which was over 1,000, definitely. Okay. Okay, so we've got, do you know any proofs for the sum of consecutive integers being n squared plus n over 2? Sure do. That lets me talk about induction. Okay, so that's going to be our final question then. So I'll rub this off. Whoops. think I broke my board eraser. Just give me a second. There we go. Okay, fab. So a proof that the sum of consecutive integers. So we want to prove that the sum of the integers k, when k is 1 to n, which, just to emphasize, is equal to 1 plus 2 plus 3 plus dot 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 plus k. And we want to prove that this is equal to, yeah, if I went forever, it would indeed be minus 1/12, Basil. And we want to know, or we want to prove that this is equal to, what have we got it up there? N squared plus n over 2. Okay, so n times n plus 1 over 2. Okay, so we're going to do this using proof by induction. So the way you do proof by induction is you show, first of all, step 1. Step 1, it's called the base case. So we show that this is true when, for a very, very small case, which is very easy to calculate. So let's consider n being 2, for example. So if we consider n being, well, I should do n being 1, shouldn't I? N being 1. So the sum of the first 1 numbers is 1. First 1 integers is 1. So we know that the sum from n equals 1 to 1, sorry, for k equals 1 to 1, if k is equal to 1, and then our formula, if we plug in the values for n being 1, gives us 1 times 2 divided by 2, which is 1. So we get 1 times 2 divided by 2 is also 1. So that's a tick. They agree. So our formula works for n being 1. So our first case, the base case. Now, step 2 in our proof by induction is to say we're going, so this is the inductive hypothesis, and this means we assume that this formula is true up to some number, capital N. So we assume true up to capital N. And what we want to prove now is, assuming it's true up to capital N, can we prove that it's also true for n plus 1? Because if we can do that, then we know it's true for 1, and therefore we've done a proof in step 2 to say if it's true for 1, then it's true for 2. And yes, it was proved by Gauss. Good knowledge. So if we know it's true for 1, then we know it's true for 1 plus 1, which is 2. But then we know it's true for 2, so we know it's true for 2 plus 1, which is 3. Then we know it's true for 3, so it's true for 3 plus 1, which is 4. And so we know it's true forever, because of the step 2. So you have to show it's true for the small case, and then you assume it's true up to some number and prove using that it's true to n plus 1. So what that means is we need to now take our sum from k equals 1 to n plus 1 of k. Right. So we can write this as 1 plus 2 plus 3 plus dot dot dot, all the way up to plus n plus 1. Okay, so I just write them out like so. But now we've assumed that this is true up to n. So that means that our formula is valid up to capital N. So what we can do is take these n numbers here, underlined in pink. So that is equal to the sum from k equals 1 to capital N of k And now, by our inductive hypothesis, we assume this was now true. So this is equal to our formula, n plus 1 over 2. So what we're left with, putting all of this together, is going to be n times n plus 1 over 2 plus n plus 1. And so now we can do some algebra. So we can factor out the n plus 1, and then we're left with n over 2 plus 1. And then we can do a final step of algebra, which is to multiply or take the factor of a half outside. So this is equal to a half n plus 1 times n plus 2. Now, we have a formula, but does this give us what we expect it to give us? So what we do is we go back to here and say, now what happens when little n is equal to big N plus 1? Then we substitute it in, and this should give us big N plus 1. N plus 1 is 2 over 2. And so the blue one here is exactly what we've got in the pink down the bottom. So we can give that a tick. And then our proof by induction is true. So just to recap, the idea is we've shown it's true for n equals 1. And then we've done the inductive hypothesis in step 2, which was saying if this is a true statement to some number, capital N, then we have shown that it must be true for n plus 1. So we know it's true for n equals 1. So by step 2, it's true for n equals 2. Go back. By step 2, if it's true for n equals 2, it's now true for n equals 3. It's now true for n equals 4. It's now true for n equals 5. It's now true forever. And we have our final proof of this formula. Okay, good question. Right, so I've seen a couple more questions. I'm afraid I am out of time. I've got some university teaching to go and do now, which is much less fun for my actual university students. But thanks everyone for joining the live stream. Thank you for submitting your questions and taking part in the chat. I'm going to be doing this every Friday at 4 o'clock UK time. So if that time is really, really bad, because I'm not sure exactly where you're all watching from, maybe you're not in the UK, but if that time is really bad, then by all means send me a message or send me a comment, and we can, maybe we can figure out another time or something. I don't mind doing that. But for now, I will be back next week, next Friday at 4 o'clock, 4 p.m. UK time. And we will be focusing the discussion, at least at the beginning. Again, I'll try and do the first half an hour based on other questions people have sent me, which will be based on our next GCSE Maths video, which will come out on Monday, so in 3 days' time. And that video is about travel graphs, so distance time graphs. And we have some fun trying to work out Usain Bolt's distance time graph. So make sure you watch the video on Monday and then send in any questions that you have. And then Bobby and Susan will answer them on Thursday. That's the Maths Appeal team. And then I'll do my live stream again next Friday at 4 o'clock. Okay, fab. Right, so thank you very much, everyone, and I'll see you soon.